And then, if you're a regular PC, you probably want to turn off restart your computer. And then you also know that I'm changing it so you upload it in assignments instead of uploading it into quizzes. All right. And then you guys also probably know your study guide for the final is these pieces and bits from the previous study guides. One of them no longer exists. I think it might be 8. There's one that I said don't do, or maybe it's 9. And you can just ignore that one then. All right. So quick review of Chapter 10 and 11. So this is a Chapter 10 problem. Well, I actually didn't have the whole problem. But this is, sorry, I tried to grab it quickly, and I guess I failed to grab the whole problem. But, you're going to do a test on data where your data is going to look something like this in terms of the fact that it has X's and Y's. And you're going to have your H0 and your H1, and you're going to have your regular critical value. So let me go ahead and give you the summary. So you're going to have your H0 and H1, which will be a little bit different than the previous ones. There'll be that rho is equal to 0, and H1 is always going to be that rho is not equal to 0. So that's our step 1. And then our step 2 will be the critical value from the PPMC table. And then you're going to draw your picture. Looks like this. Put in your value from the PPMC table, shade that way. You're also going to do a -1 and shade this way. Because remember, this goes from -1 to +1. So then these are your critical values here. All right, so the shaded areas are guilty regions. The non-shaded areas are your not guilty regions. And then you're going to put your data into list 1 and list 2, and you're going to do that stat test linear t-test. That's going to give you your R, right? And R is what you're going to use to compare into this table that you've made for the critical values. Just to make sure everyone's kind of on board this table down here. And then you decide whether or not to reject H0. If it's in that guilty region, the shaded region, right, if it's in these regions here, then you're going to reject H0. If it's in this middle part, then you will not reject H0. And the last part is, I'm just going to summarize it for your claim of variables. And that's as simple as saying this. There is or is not enough evidence. There either is or is not enough evidence to say there is a correlation between blank and blank. And that's all you need to do. That's as straightforward. I'm going to be really, really simple in all these sections, but that's all you got to do for this one. There either is or is not enough evidence to say there is correlation between blank and blank, whatever your X and Y is. Questions on Chapter 10 stuff? Okay, the other thing, yeah.
Do you give us the R, or do we have to find out the R? Because some problems
you find the R.
Also?
You find the R. So you're going to use this to find the R. The test statistics.
Do we have to find the p-value also?
Nope. You just have to have R.
Okay.
Professor Young?
Yes.
For step 4, if your are both within the shaded area, you reject H0?
Yep, exactly. Remember, this is the guilty area. So the shaded areas are the reject H0. The middle areas, they do not reject. Not guilty, not enough evidence. So you want to put shaded area. Unshaded area. So that's where those two kind of come in. This will be the shaded area. And this is if it's in the unshaded area. Other questions about this?
Are we going to have to identify the claim for this one
nope.
or no?
Nope. Nope. So we'll say summarize. How's it sound? And this is really just, should be R. The test statistic, we're using R for our test statistic. And you don't have to worry about the p-value. There. And this again is rho equals 0. Rho is not equal to 0. That's not really useful. No. Okay. And then there's a second part of this, which is that you are finding some linear regression line and approximating something, right? So you're going to approximate the income for 40,000 cars, which means that you have to figure out whether this is X or Y. This is going to be X. This is my X, right? Because it's cars, and cars are my, I look down here, cars are my X, so it's my X. So then if I put, you have to use that, either use a linear regression line if your data is a line. In other words, if you rejected H naught, and if you did not, oh, I didn't do that. Let me see if I can pull up. Did I keep one of those? No. Hold on. Recent? Just have it up here. It's worth mentioning. It's worth bringing this up for. Oh, and you guys are good with this one too, right? The correlation. Evan's all good with where those all go. And remember that it goes from -1 to +1. It does not go. You can't have anything larger than -1 or +1. That's as high and low as it goes. Okay, I guess that's all right. So this is our regression line. We get it from our stat test, linear t-test. We get A and B from there. But you can only use it if you reject H naught. So if you do not reject H naught, how do I get this as my color? If you do not reject H naught, use this instead. Right? You can use the sample mean, y bar. And I'll put that one, y bar, the average y. So that's kind of the basic concept, is if you reject H naught, then it is a line. Kind of set. I should have found that slide. That would be better. Maybe it's in here. Hold on. Sorry guys, I've been kind of going crazy trying to get the exams written, so I have not. I had it written down great in one spot. I don't know what I did with it now. Oh, maybe this is it. Right, here we go. Here it is. So use the line when you reject H naught. So if you reject H naught, it is a line. If you do not reject H naught, then it is not a line. So you use average y to predict. Maybe that's clear. Is that are you guys totally all over this, or do I need to explain this more? So when you reject H naught, you're saying it is a line, because here's your line, right? And here's your critical value. So this is your rejection region. If I get something out here, then I'm saying it's close to 1. It's close to a line, which means that the regression line makes sense to use to predict it. However, if I get something that is, here's my thing here. If I get something that's over here, then my data is not a line. So it doesn't make sense to use this regression line to predict it. It makes more sense to just use the average y to predict. Does that make sense? Because this is perfect line.
Yeah.
These two here are the perfect lines. And this spot here is total chaos. That means it's, how do you use the average y? Okay, so like in other words, we all agree that there is no correlation between height and test scores. Is that correct? Does everyone understand what I'm saying? So my best predictor for someone who is 6'8", what score they got on their test, is just the class average. That's my best guess. How do you do that? You find the average, or y. How do you, so in other words, here's the question we had. Approximate the income. If these two things were not correlated, and then I'd say, well, for 40,000 cars, if there's no correlation, then I would just take these numbers and I'd average them and find the y bar. Does that making sense? So how do you do that? Remember, we do stat, calc, 2 var stats. of L1, comma L2, and that gives you your y bar and your x bar both. Let me get rid of this one. This is in my way. This is in my way too. What's this one? Okay, so if I pull up my handy dandy, okay. Do you guys need me to show you, or is everyone kind of alright with that? So if I go stat edit and I put stuff into here, I put stuff into here, and I go to stat calc 2-bar stats of L1, comma L2. It will totally give me, it gives me my X bar. If I arrow down, it gives me my Y bar as well. Okay, good. So let's go ahead and move on. So this is another problem. This is a different one. Now we're into chapter 11. And chapter 11 talks about, it's something needing something. So you have observed, but my observed are just, there's only one row of them. There's not a whole matrix of them. So in this case, my observed are just this strip of information right here. So when my observed are just a list, that's when I know I have a chi-squared list and not a chi-squared matrix. How do I know I have a chi-squared at all? Because I have labels up here and labels there. Or maybe I just have labels up here, but I don't have lists. If I had stuff going all the way down here and stuff going all the way down here and nothing here, then then that looks like an ANOVA, right? 3 lists. If I only have 2 of them and we have stuff going down here, yeah, actually I'll talk about that. I'll talk about that in 5 minutes. But this one is when you have just the list and you have some observed. So what do you do with it? You have to compute, you always have to compute your expecteds. So here, my expecteds are going to be a certain percentage of the total for each category. So this would be, my expected would be 74% of the total would go in here. 16% of my total would go in here. 10% of my total would go in there. The other possibility is it'll say equally likely and not give you percentages. It's either going to give you percentages or it's going to say equally likely. If it's equally likely, you take the total and you divide by how many categories you have. You put an equal amount in each category. This is the summary of how this works. My step 1 is O sub I equals E sub I. My H1 would be, my H0 is O sub I equals E sub I. My H1 is O sub I is not equal to E sub I. My critical value, I find that from my chi-squared table, and then I draw this picture that goes straight up, kind of almost straight up, and then kind of curls out. And remember, it's only ever right-tailed, because this starts at 0, and it never goes negative. So it starts here and starts here at 0 to 0, and just goes in one direction. And then I calculate my test stat. I take every observed value minus the expected value squared divided by the expected, and then I add them all up. So back here I find each one of my observed. Right, so in this case, my observed are 62, and then 23, and then 5. And I find my expecteds, whatever they are. So that might be 74. Looks like this is actually 90, 80, 90, 100. Yep, I got lucky. 74, and then this is 16. Luckily, I picked an example that happened to have an exact number, the 80, 90, 100. And then what you'll do is you'll do every observed minus its expected, right? So 62 minus its expected squared, and then you're going to divide by the expected. And you'll do that for every single one. You'll do that for this one, you'll do it for that one, you do it for that one, and then you add them all up. I do actually want to see this work of you showing that you know where this comes from. You do one for that one. You do one for this one, and then you just add them. You would add them all up. Okay. Questions on this one? Call it out or ask. And then you'll throw it in here, right? If it's over here, then you're going to reject the null hypothesis. If it's over here, then you would not reject the null hypothesis. And then summarize your findings for the claim, and this is just as simple as saying blank evidence that the proportions are equal to what expected. Okay, so I should probably mute everybody. Okay. Good. And that's kind of all you have to do. Blank evidence, either there is or is not enough evidence that the proportions are equal to what expected. And you can use that same one for both chi-squareds. So this is the other chi-squared. It looks something like this. This is a matrix. It's kind of obvious because you can kind of see that you have who keeps muting themselves, unmuting themselves. Okay. So we have data here. Right, we have labels there, we have labels there, we have labels on both sides, then you have a matrix. So that's the chi-squared matrix, which is kind of the easiest one to spot. You have to remember that you have to have data, you have to have labels on the top and the side both. It's the only way that it's a matrix, is you have labels on the top and you have labels on the side. Just think about our puppies in the pound, or, you know, the rescue. So for this one, steps are also pretty similar. You can just, step one is H on H1. You can just say, again, if you want, that O sub I equals E sub I. And then for this one, you can always say that O sub I is not equal to E sub I, just like you did for the other chi-squared. And then it's a chi-squared, so you're going to use the chi-squared table. So you're going to use the chi-squared table. Look it up. And you're going to draw your picture, which is, again, going to look the same. It's going to look like that. Degrees of freedom is the number of rows minus 1 times the number of columns minus 1. The nice thing is, when you put your data in, it will compute it. It'll kind of compute it for you. So you will need to compute the first and last expected values. So this is how you compute it. You take the row sum times the column sum divided by the grand sum. So for this one, I take his row sum multiplied by his column sum divided by the grand sum. And you define it for the first one and for the last one as well. Just the first and last, just to prove you know how to do it. And then the other part of step 3 is just putting that data into a matrix. So you'd say, okay, well, here's my data. Put it into matrix A. And so I'm going to turn it on. You go to second matrix. Go over to edit. Hit enter. Because if you just do this, it's just going to give you A. And it'll tell you what's in A. There's nothing in A. But if you do second matrix and you go to edit, that's when you put something into A. So let's say this is a 3 by 3, so 3, enter, 3, enter, and then just type in your data. So 4, 2, 6, 1, 5, 9. And make sure you double check your data, because if your data is wrong, the whole thing's going to be wrong, and you won't even know it. Then you just go to stat, test, chi-squared test. Incidentally, some of you will have this goodness to fit test, which you can use for 11.1, but everybody doesn't have it, so that's why I'm not going to show you guys. But you can use that. You just put your expected, your observed into list 1, your expected into list 2. This one here, you just put your observed in list A into matrix A. Your expecteds, you don't put anything into B. It puts something into B. It's going to store it into B. You just go to calculate, and it gives you your chi-squared and your p-value. So then you figure out what your chi-squared is. You stick it into your picture. And if you're in the guilty range, the shaded range, then you reject H0. If you're in the non-shaded range, then you do not reject H0. And then step 5 is either enough or not enough evidence to say. You can just say you have to reject the claim. You can just write say. The proportions are equal. That's close enough. We're staying very informal with this one. Don't worry about the claims, just enough evidence or not enough evidence to say that the proportions are equal. That's it. Formula for the expected value, yes. So the expected value formula is right there. Row sum times column sum divided by the grand total. It's just this one times this one divided by that one. That's it. It's also in your notes. It's only in the notes. Okay. Now, the next thing we talked about was ANOVA. This is ANOVA. How do you know it's ANOVA? Because you have categories. You have 3 or more categories along one side, and you have nothing along the other one. You don't have any categories at all along the other way. So it might be that you have categories along the sides and nothing across the top, but you have it on one side, either the top or the side, but not both. And if it's 3 or more lists, then it's ANOVA. If there's only 2 of them, then it's probably chapter 10. They'd be matched up pairs. But this one we're comparing means. So this is all about the means. So there'll be talk about means in here. And what do? You're saying that one mean equals the next mean equals the next mean equals the next mean. All the means are equal. And then H1 is at least one differs. You can't say that H1 is not equal to, mu1 is not equal to mu2, is not equal to mu3, because you don't know which one. At least only one of them may differ, and you don't know which one. So just say at least one differs. Step 2, just write down your alpha. That's it. Step 3, compute the p-value. Put the groups each into a different list. Do stat test ANOVA of list 1, comma list 2, comma list 3, comma list 4, however many lists you have. And then you'll get your p-value. And remember, this is all about whether or not your sample is unusual. A small p-value means you're unusual. So you're going to reject if your p-value is small, less than alpha. Typically, our guideline for unusual is 5% or less. If it's alpha can change. Typically, alpha is 5%. So as long as your p-value is alpha or less, then you're going to reject because it's unusual. So again, this one is you reject H0 if p-value less than alpha or equal to, but that's not actually going to happen, so that's fine. And then step 5 summary. Either you have enough evidence or you don't have enough evidence. That means to say means are the same. That's it. Very, very straightforward. It could be more complicated, but we're just going to handle it in a very, very straightforward way. All right, so that we've now wasted half an hour going through the summary of chapters 10 through 11, which I did not intend to do, but it is really important because it's a big part of your exam. Now we're going to spend 20 minutes, 15 minutes, which I did intend to do, to talk about how to tell them apart, because you need to do that. Right, so I did this in class already. I'll talk about it quickly again. But you have kind of 3 different sections, technically 4 different problems. So you have your chapter 10, which is when you have 2 data, you have 2 variables, and they're numerical. And there's an x and a y. And there's 2 parts to that one too, because the first part is going to be the hypothesis test. The second part I'm going to ask you to predict. There's a prediction thing. And then you have the second part, which is the chi-squareds. And there's 2 of them. So the chi-squareds are going to be, they're going to have the list, and you got the matrix. And the matrix is kind of easy to spot because it's a matrix. There's categories across the top and the side. And this one, there's only categories along one, and then along the other is observed and expected. Typically, it's categories across the top, and then observed and expected along the side. Or there might not be anything at all, and you have to make your own table. And again, this one is categories. So you're talking about frequencies in the categories or proportions, and you have observed and expected. So that's kind of the key things to kind of cue into there. The last thing is ANOVA, which is kind of, I think, the easiest one to spot because it's 3 or more lists. There's only categories or labels along the top or the side only, and then a long list, then a string of numbers after it or below it. And that one's, also very, very straightforward. We're just doing it in kind of very simple sort of way. Another way you can tell it is just looking at the variables. How many variables do you have, right? And that doesn't mean how many categories you have. It means how many variables you have. And then if your variable, the answer to your variables are categories, then it's a chi-squared. If it's 2 variables, then it's a chi-squared matrix. If it's 1 variable, then it's a chi-squared list. If your variables are numbers, if there's 2 variables, then it's PPMC, linear regression, right? And you find your R, compare that to your PPMC value. If it's 1 variable and the answers are numbers, but you have different groups of them, then that's ANOVA, where you have 3 groups. There's only 1 variable, but there's 3, it looks like categories, but it's really 3 groups. And then each one has data inside of it. Right, and then we kind of talked before about figuring out which one is, right, just from looking at them. So when you have categories just here, right, so these two, you can see there's only categories in one direction. There's not categories on the sides. There's nothing on the sides. So these 2 are the ones that are not chi-squareds. You have these lists, but there's nothing along the side. It's only on the top or the side, but not both. So if there's 2 of them, they're matched pairs. This is going to be your chapter 10. If there's 3 or more, this is going to be your ANOVA. And then the chi-squares are going to be where you have stuff, you have categories here and here. These ones you may have to write in yourself. But this one is the matrix. And this one, this is not really a matrix because this is observed and expected. So it's really just this here, chi-squared list. And again, the chi-squared list, I might just give it to you in text, and you have to create this table yourself. It's entirely possible. In both cases, you have to compute the expected values. This one, you have to compute all of them yourself. This one, you only have to compute the first and the last expected values. All right, so we're going to go through maybe 10 slides on how to tell them apart. What kind of problem is this? So here's the first, actually before we do that, my bad. Just want to talk about some common mistakes people made on exam 3. Right, you need to be able to tell the difference between a proportion and a mean. A mean will literally say mean, always, or average, mean or average, right? Or it might have an X bar, which would be the same thing as a mean. So it'll say X bar equals, if it says X bar equals blah, then that's saying it's a mean. And the other thing people screwed up is not realizing that a proportion, I'm either going to give you X, the number of successes, or the P. Rarely will I give you both. And they're not the same thing. So if you have a percentage, you don't put that over your total. That's not, you can't have that many successes. And a lot of times people would screw up and forget that they used a T table and should use a Z table and vice versa. So remember, means, you use a T table, mean Mr. T is the way to remember that one. And if it's easy peasy is the way of remembering that proportions use a Z table, PZ. And then, also just make sure you always give me the whole test, all 5 steps on that piece of paper. You have to write out everything. And if I ask for a confidence interval, you have to give me the whole confidence interval, not just the margin of error that you're typing in. Okay, so let's go ahead. Oh, right. I don't want to do this yet. I'll do that one later. Whoa, where am I? Oh, yeah, I guess we'll do. All right, so you do need to know how to do a tree. We're going to go over those actually at the end. So let's go over this problem though first before we get going, because this is really important in case people drop off before things happen. So weights of rats have a mean of 115 grams and a standard deviation of 16 grams. What's the probability a rat weighs less than 112 grams? And I actually would tell you that assume this is normally distributed. Assume normally distributed. Okay, so then you might say, well, I don't have enough information to do a test of any type. So, and you also know that, remember, you're getting your information on the exam. I'm going to organize it where it's exam 1 material, then exam 2 material, then exam 3 material, then exam 4 material. Or you might be in the opposite spot where it goes exam 4 material, then exam 3, then exam 2, then exam 1. So you're going to kind of have a sense of what group you're in. So you'll be like, well, I know I'm not in group 4 anymore. I might be in group 3, or I might be in group 2. I'm not sure. Or I might be in group 1. Those would be kind of your options. And you kind of get a sense of where you're at. But this is not going to be the first exam, so it might be the third or the second exam. And you'll kind of say, well, this is not a hypothesis test or a confidence interval, so it must be exam 3, so then, okay, that's normally distributed. So then you're going to, remember you got your 4 steps. Your first step is going to be find your z-scores. The second step is going to be draw a picture. And the third step for this normal distribution is going to be use normal CDF to find the area or the probability. Those are the same thing. Remember, area and probability are the same thing. So in this case, I would find my z-score. So I'd say, okay, well, here's my mean. That's my, rats in general have a mean, so that's not my sample mean, it's my general mean. Standard deviation of 16, that's my sigma. And then I want to know, this is what I'm asking about, this is what I care about, this is the probability, right? So the probability, that's going to be my x value. So I'm going to use that whole z equals x minus mu over standard deviation, and I will get 112 minus 115. Oh, why am I doing this? You guys do it. You guys do this. In fact, you guys do all this. So, take a picture of this. I'll pop you guys into groups. I'll give you guys, and then do the one below it too. This one below as well. See who we have. I've got no one who's really together. Oh, you guys are together. Jelena and Angela, are you usually with Beatel? Is that right? Beatel are usually in that. Are you the 2 o'clock?
Yeah.
Okay, yeah, good. I'll put you guys together and maybe I'll put J in there. Or I'll put Angel likes chocolate. I'll put Angel in there. And then Jake, J. Those guys. So all right. So if you guys want to pop into groups, you can. And I'll just give you another maybe 3 minutes to sort this one out. But it will say normal distributed, so that will help. So that's kind of your key for how do you know it is. It'll say normally distributed. Angel, if you want to jump in and maybe, see if people have questions. Kara, Erica, do you guys want to hop in to your regular group?